All right, I had a question about von Mises's failure criterion, but I'd like to first just start off with reviewing failure theories in general and talking about what we've learned already about tensile stress strain curves. So before we get into that, let's talk about tensile stress strain curves and how we know something has yielded or not based on what goes on for a particular state of stress in a tension test. So if you remember, for a stress strain curve, we plot stress on this axis and strain on this axis. And a typical ductile material will go linear elastic to a certain point where you get to the proportional limit stress, and it starts to curve a little bit. You get to the yield stress, which often is the same as the proportional limit stress. Then after it yields, it can kind of curve for a long time. It gets to some ultimate stress over here, and then it finally breaks at this point. So this would be the fracture strain. All right, so we go through and we do this and we estimate what the yield stress is. It would be right around here. And this would be for a ductile material. And in our tension specimen, we have what's called a uniaxial stress state. So on my little stress block or my stress element, I have stress just in the vertical direction when I pull on this bar in my testing machine. When that stress in the vertical direction reaches sigma yield, then I know that my material has yielded. And if I have if I'm analyzing a structure and I see that stress is at sigma yield, then I can say that material has yielded. But the catch is that only works if you have a uniaxial stress state. Similarly, for brittle materials, stress strain curve starts out very similar, linear elastic. For brittle materials, there tends not to be much curvy part to the stress strain curve. It tends to break, and you reach this ultimate stress when it finally breaks. So the point of this is, if you have a ductile material, they tend to fail because of shearing stresses. If you have a brittle material, those tend to fail because of normal stresses. So these are taus and these are sigmas. Now, if you look at the stress strain curve, obviously this is a sigma, but what we're going to have to do is we're going to have to relate this sigma back to a shearing stress in this case. All right, so let's talk about the first failure criterion for ductile materials, called the maximum shear stress theory of failure, or what's also known as the Tresca criterion. And now what we're trying to do with yield criteria is to take a complicated stress state, like the one that I have pictured here, and determine whether or not that causes yielding in the material. So for this example, let's say that we have a yield stress for this material equal to 120 megapascals. And if we look at this picture, none of those stresses are above 100 megapascals in this picture. But that doesn't mean that the thing's not going to yield. We're going to have to use the yield criterion to figure out whether or not the combination of the stresses off at any angle in this material causes this to yield. So we're going to start off with 4 ductile materials, something known as the maximum shear stress theory, or the Tresca criterion of failure for ductile materials. And in this, what we want for our stress state is to find the maximum shearing stress. We know this from Moore's circle as tau maximum absolute. All right, so we have to construct a Moore circle. Let's go ahead and do that. I'll do the best I can to make this picture look okay. Let's see. Let me try a little bit better. Maybe move my line over here a little bit. We're going to plot our x point, which in this case is going to be 50, 30. Remember, positive tau was plotted downward. Center of our circle is at sigma average, 0. That would be 50 plus negative 20 over 2. That's 30 over 2. That's 15. So this is 15, 0. Over here on the other side of the circle is my y point, which would be minus 20, minus 30. And what we need to do is we need to find, for the 2D circle, what the radius of this 2D circle is. So I'm going to drop this down. That's 30. And this distance, I believe, would be 35. Let me grab my calculator, and I'll check that. Okay, so that distance is 35. And the radius we can find because r squared is equal to 30 squared plus 35 squared. Okay, and I got 46.1. In this case, it would be in megapascals. So our principal stress, let's go ahead and find that, would be 15 plus 46.1, 61.1, and sigma P2 would be 15 minus 46.1. That would be minus 31.1. Now we have to be careful because we did find r, which is the radius in the xy plane, but we need the absolute maximum shearing stress. So I need to plot one more point, and sigma P3, 0, which is sigma z, 0. And in this case, it happens to be to the right of the circle. So this point would be 100, 0. And we make 2 additional circles. It's hard to draw on this tablet. Sorry for the poor looking circle there. Let's see if I can erase a little bit of this. And tau maximum absolute in this problem is the radius of the biggest circle. It's 100 minus a negative 31.1 divided by 2. And that turns out to be 65.6 megapascals. All right, now we're given the yield stress of the material up here is 120 megapascals. And we have just computed the maximum shearing stress, the absolute maximum shearing stress of 65.6 megapascals. This is a sigma and this is a tau. We can't really compare those directly. What we need to do is we need to figure out what tau maximum absolute is in a tension test at yield. If you remember back to the previous page that we had our uniaxial state of stress. I'm going to draw this in the red color. And when it yielded, it was sigma yield in the vertical direction. The Moore circle for this state of stress we plot sigma x comma tau xy, which is this point, and sigma yield comma 0, which is sigma y comma tau xy is this point. The third principal stress is 0, so it plots also at 0 comma 0. Well, the radius of this circle which is tau maximum absolute for the tension test, happens to be sigma yield minus 0 over 2. Sigma yield minus 0 over 2 for our material properties is going to be 60 megapascals. And we take a look now, 65.5, keep saying 0.5, 65.6 is greater than sigma yield over 2. So this stands for, therefore, the material yields by this failure criterion. All right, so that's an example of using the absolute maximum shearing stress theory for ductile materials. Now there's another theory that we learned in class for ductile materials called the maximum distortion energy theory, or the von Mises criterion. And that involves the application of a formula to come up with what's called an equivalent stress. It's called the von Mises stress. And you compare that to that critical stress in a tension test when the material yields. I'm going to present the formula next and how to come up with the von Mises stress and apply the failure criterion. And then I'm going to go back and show you where all that equation comes from. You're probably most interested in the application at this point. So let me clear off a little bit of space. I'm going to pause it here for just a moment. All right, so I'm going to write down what's called the von Mises stress equation here. Like I said, we'll talk about where it comes from in just a moment. It starts off with 1 over the square root of 2, and then we have the differences among all of the normal stresses squared plus 6 times each of the shearing stresses squared. That quantity in the brackets is taken to the 1/2 power. It looks like an intimidating equation, and there's a lot going on, but there's kind of a nice symmetry to it. Kind of repeats, and you kind of see the pattern. I will not ask you to memorize this equation, but if you do know this equation, you don't have to do a Mohr circle. In order to apply the von Mises criterion, you just plug these numbers into this equation. And so in this case, what's known as the von Mises stress would be 1 over the square root of 2 sigma x minus sigma y plus sigma y minus sigma z, which is 0, squared, plus sigma z minus sigma x, quantity squared. And then, actually we do have a sigma z, I'm sorry. Let me back this up just a little bit. Let me start over here. Sigma y minus sigma z plus sigma z minus sigma x plus 6 times the shearing stress squared. The other shearing stresses are 0. Okay. So now let me get my calculator back out and calculate what the von Mises equivalent stress is. So 50 plus 20 is 70. I'm going to square it. Minus 20 minus 100 is 120 squared. And then I have 100 minus 50, that's 50 squared. Then I have 30 squared times 6, and add that in there. I'm going to take the square root of that, and then I'm going to take and I'm going to divide that by the square root of 2. And what I just got was 116.6 megapascals. Okay, now what we need to do is we need to compare this to the von Mises stress in a tension test when the material yields. Let me switch over to my red color again. And like before, in a tension test, we have a uniaxial stress state. When the material yields, the stress in the vertical direction is the yield stress. The von Mises stress can be found by applying this same big long equation to the uniaxial stress state. Sigma yield minus 0, 0 minus 0, and we get another sigma yield squared term. All right, so if we add these two together, we get 2 sigma yield. If we take the square root, we get square root of 2 sigma yield. And if we divide that by the square root of 2, well, what this works out to be in a tension test, the von Mises stress at yield is sigma yield. So what we're going to do is we're going to compare the von Mises stress from our multi-axial stress state. That's the blue stress state, which is 116.6 megapascals. We're going to compare that to what we just found, that I'm going to put a question mark here. Is it greater than or equal to 120 megapascals? All right, so if we look at this, it's not. So this theory says it does not yield. There are two different theories. They can give you different results for very special states of stress. This is a kind of a special state of stress where one theory says that it will yield and the other theory says that it will not. Sometimes both of them will tell you no, sometimes both of them will tell you yes, and then sometimes there's this particular region of stress values where things kind of lie in between. All right, so that's how you apply the von Mises criterion. On an exam, on your final exam, you can use either failure criterion that you want for ductile materials. I will grade whichever theory that you use, so you can use either one. The important thing is to justify your result as to whether or not you say that the material yields or not at that particular location. All right, now let's go back and let me show you a little bit of background on where the von Mises stress comes from. All right, so the name of the theory is called the maximum distortion energy theory. There's a couple things we want to pick out of there. The term distortion means shear, and then there's the energy part. Let's review a little bit about energy, and then we'll talk about distortion. You might know from physics class that the energy stored in a linear elastic spring is the area underneath of the load deflection curve. Of course, that slope would be the spring stiffness K, and we would find it by taking 1/2 the maximum force times that displacement. But since F is equal to Kx, we can also write this energy term as 1/2 Kx squared. So we can write it in terms of all displacements if we want. If we want, we can write it in terms of all forces. Now let's talk about a bar. So let me make a sketch. This is for a spring. Let's talk about what happens in a bar of material. It's hard for me to draw straight. When we have this material in a tension test, it kind of behaves just like a spring. But we take a look at the stress-strain curve. And up until you get to the proportional limit, which is pretty close to the yield stress for a ductile material, you have a straight line relationship, and we call the symbol for the slope E, the modulus of elasticity. And we can also compute something that's underneath this curve. And the area underneath that curve would be 1/2 sigma times epsilon. And if we look at the units of sigma and epsilon, because stress is force over area and strain is the change in length divided by the initial length, we have a, let me get my initial length. I jumped ahead just a little bit. What we have on top is force times distance, which is energy, divided by area times length, which is volume. So this is known as an energy density term. So the area underneath of a stress-strain curve is called the energy density. Just like we have mass density, or weight densities or mass densities, something per volume is called a density. All right, well, in a multi-axial stress state, the total energy density, which we're going to use the symbol U for, is the sum of the principal stress-strain energy densities. And the symbols, subscript 1, 2, and 3, represent the principal stresses and the principal strains. Just like we can have expressed the energy stored in a spring in terms of the displacement or the force and the spring stiffness, we can use Hooke's law to represent this energy density. And then we would have it in terms of the modulus of elasticity, Poisson's ratio, and all of that. So without doing the algebra, I'm going to write down this by 3D Hooke's law. I can rewrite this energy density term in terms of only stresses as this. It's kind of a long equation. But here we have some of the normal stresses, principal stresses squared. We have Poisson's ratio. And then we have this kind of combination of multiplying principal stresses to each other. Now, this theory is called the maximum distortion energy theory. So what we want is the distortion energy. And this total energy is actually composed of two parts, a distortion energy part and what's known as a volume change part. Because we're looking at ductile materials that fail because of shearing stresses, we want the distortion part. And it turns out that the distortion part of this is 1 over 12G, where G is the shear modulus. And then we have differences among the principal stresses squared. Okay, here I have used the relationship that G is equal to E over 2 divided by 1 plus nu. There's more than a page of algebra to get from this step into this step. And likewise, there's a lot of algebra from this step into this step. I just want to show you the highlights. We're interested in the application, but I do want you to see where it comes from. All right, let me make a clean page, and I'm going to copy that last line down again. Okay, so what we have in this line is the distortion energy stored in the material. Now the theory is that when you have a multi-axial stress state, you can compare the distortion energy for that multi-axial stress state back to the distortion energy in a tension test when the material yields. And just like we've talked about before, when you have a tension test, you have a uniaxial stress state, and when the material yields, that stress is equal to the yield stress. So the distortion energy from a tension test at yield is going to be equal to 1 over 12G sigma 1 minus sigma 2 squared. The others are 0, so it's sigma yield squared. Sigma 2 minus sigma 3 minus sigma 1. So we get another sigma yield squared term. I'm not going to divide through by 2 for reasons that we'll see in just a moment. But the distortion energy then at yield is 2 sigma yield squared divided by 12G. So when this value equals this value, we have an equivalent energy state in our more complicated stress situation. Let's equate these two. 1 over 12G times 2 sigma yield squared is equal to this complicated stuff on this side. I'm going to go ahead and write it again. Take me just a moment. Okay, and if you notice now, the 1 over 12G's cancel out. And I have this 2 sitting over here. Actually, what I'm going to do is I'm going to move that to this side. And I'm going to divide everything. I'm going to divide it by 2, and then I'm going to take the square root of both sides. So what I get over on the one side is 1 over the square root of 2, and then I have the differences among the normal principal stresses squared to the 1/2 power, and over here I have the yield stress. So I've divided by the square root of 2, and I've taken the square root of both sides. This left-hand side in this equation that I have written here is known as the von Mises stress. And we said that it is distortion energy. One interpretation of distortion is shearing stresses. If we go back to a 3D Moore circle, each local maximum shearing stress is the radius of each of these circles. The radius is the diameter over 2. And look what we have in these terms. If you take the square root of 2 and you bring it under the square root symbol here and into these, we can get a sigma 1 minus sigma 2 over 2 term in each of these. So this is kind of a combination of all three local maximum shearing stresses. That's why the Tresca criterion and the von Mises criterion don't give you the exact same thing. This is a combination of the three, whereas the absolute maximum shearing stress only uses one of them. Now there's another way to write this left-hand side. If you do a lot more algebra, you can write this in terms of coordinate stresses instead of principal stresses. I'm going to write that down for you here. 1 over the square root of 2. Now we have the differences among the normal stresses squared. And it doesn't matter if you reverse these on accident, if they're under the, if you're squaring both terms. But if you're not in the principal stress state, you have to include the shear terms. Of course, when you are in the principal stress state, the shear terms are 0. All right, so that's how we get this failure criterion if what you calculate for your multi-axial stress state is greater than or equal to the yield strength, then the material is predicted to yield. Yielding is important for a couple of reasons. If you're manufacturing something, you may want it to yield, so you may want it to be above this level of stress, like stamping out door panels for a car. Or, in some situations, you want to be well below the yield stress of the material. It's also important to note that if you yield the material, Hooke's law that relates stresses and strains no longer applies. You have more sophisticated stress-strain relations after that material yields. And again, I just want to emphasize that on your test that I would give, I would always let you choose whichever failure criterion you would like to use for ductile materials. We have our choice between this one, the von Mises criterion, and the Tresca criterion. I will grade whichever one that you apply to your situation. Now we have one more that we want to talk about, and that is for brittle materials. Let me save this page. And we talked at the beginning about how brittle materials fail because of high sigmas. And this is called the maximum principal stress criterion. So I would have to say in a problem statement that you have a brittle material and it has an ultimate strength of something. Let's say it's 200 megapascals. And I would have to give you a stress state. We can go back and look at the stress state that we used earlier. The way that you apply the maximum principal stress criterion is that you simply find your biggest principal stress magnitude. So I'm going to write it this way. What this means is you find sigma P1, sigma P2, and sigma P3. You take the absolute value of them, and then you choose the largest. If any of those are greater than or equal to the ultimate strength, then the material breaks. It's predicted to break. All right, so if you remember in our previous example, we had a maximum, well, let's list all three of them. In our previous example, using that stress state, we had sigma P1 was 61.1, sigma P2 was equal to minus 31.1, and sigma P3, which was sigma Z, is equal to 100. If I look at these, the biggest magnitude is 100. And so I do a comparison. Is 100 greater than or equal to 200? So in this case, no, not predicted to break. All right. So that's pretty much all there is to that. Now, there is an assumption that we're making about the material in this particular situation. The assumption is that we have what's known as an isotropic material, behaves the same in all different directions, and it also behaves the same in tension and compression. Some materials, that's a very good assumption for. Other materials, it's not, like concrete. Concrete has very different strengths in tension and compression. There are special failure criteria for accounting for materials like concrete. There's some in the book. There really aren't any homework problems over that. In our class, we're just going to cover these failure criteria.